So last video we talked about graph isomorphisms. And remember, this is our way of saying that two graphs really are the same graphs in terms of their structure, right, regardless of how they're labeled. Now, in this video we'll talk about some other graph theory terms, subgraphs, and complements that actually could help you determine whether two graphs are isomorphic or not. Well, complements maybe not so much, but subgraphs will help you. And what is a subgraph? As the name suggests, it's basically a graph contained in your graph. Okay, so I'll draw a picture here. So let's say I gave you, and so this graph on 8 vertices. I'm going to draw some edges here, some edges here, maybe one more. Okay, whatever. So a subgraph of G is essentially any graph contained in G, right? So for instance, this is a C4, right, or a 4-cycle subgraph of the graph G. Now, if you look at the definition here, right, formally, what we're really doing is to create a subgraph G prime. We're picking a subset of vertices, right? So V prime here consists of these 4 vertices. We're also picking a subset of edges of G such that those edges must only connect to vertices that you've already picked in V prime. So that's true here, right? This edge, this edge, this edge, this edge. What the third condition just says here is that I can't pick this edge, for instance, one on the upper right. And that's because I didn't pick these 2 vertices, right, to be in my subgraph. So you start with the vertices and you fill it up with some edges. Now, you don't have to take all the edges connecting your vertices in V prime either, right? So my original graph here, G, could have had an edge here, for instance. I would still say that we have a 4-cycle as a subgraph, right? Although I can also have taken this edge, and now that's also another subgraph, right? But hopefully you get the picture there, that you're not required to take all the edges connecting all the vertices in V. There actually is another type of subgraph that we won't be talking about specifically. It's called an induced subgraph, just in case you're wondering. Induced subgraph. Let's see, my handwriting here is induced subgraph there. Right, and that's where you pick a set of vertices and then you just pick all the edges that were already there in G to be in your subgraph as well. Right, but yeah, you don't have to worry about that. Just working with general subgraphs here. Now, where this helps us in terms of graph isomorphisms is the fact that if you can find that in one of the graphs, it has a certain type of subgraph, say a cycle or a complete graph as a subgraph, but then on the other graph, right, in the other graph, you don't have that type, then you can safely say that the two graphs are not isomorphic. Okay, so here's an example. H1 and H2 are both graphs on 8 vertices, and in fact, they actually have the same degree sequence. Right, and so even looking at degrees, we're not able to conclude that they're not isomorphic. Right? Remember, just because they have the same degree sequence doesn't mean they are isomorphic. It just means we can't discount, right, the fact that it may not be. But look at the subgraphs here. If you look at the graph on the right here, H2, I can pick vertices 1, 2, 3, and 4. And I can see here that there is a K4 subgraph of H2. K4 being the complete graph for 4 vertices. Right? You start with 4 vertices and connect all of them using edges. If you look at H1, for any 4 vertex subset, well, we're not going to get a K4. Or in other words, you're not going to be able to find any 4 vertex subset in H1 such that all of them are connected to one another. Right, so you can also say they will not all be connected. Okay, let's do this properly. Let's say adjacent to each other. All right, so this is what I was talking about before in a previous video. The words connected and adjacent means something specific in graph theory, right? So the correct term here is to say adjacent and not connected. Okay, but therefore, now we can conclude H1 and H2 are not isomorphic. Right? They can't be. Because if there were an isomorphism, then these 4 vertices 1, 2, 3, and 4 in H2 must be mapped to some 4 vertices in H1 that are also connected using a K4 subgraph. And that's just not true here. Right, so that's pretty nice. It gives us another tool that we can use in order to show that 2 graphs are not isomorphic to one another. Complements is another definition that I want to talk about here. And again, for a lot of these graph theory terms, right, their names give you some hint as to what they mean. Right? Complement. What does complement mean? Remember from high school geometry, you probably remember what complement means in that context. What is the complement of a 40-degree angle? Well, its complement is 50 degrees. Right? It's what you need to add to 40 to get to 90 for your total. Right? And so a graph complement is basically another graph on the same vertex set consisting of all the edges that are not there in your graph. Okay, so what do I mean by that? If you look at the graph here on the left, that's my graph G. And I'm trying to draw here my complement G bar. Now, 5, 6 is not an edge in G. So in my complement, it is. Okay, 4, 5 is an edge at G, so it's not an edge in G bar. And so you basically just have to go through all the missing edges in G, right? The edges that, if you add all of them, it would make G a complete graph. Right? So what are the others? 5, 6, 5, 1 is not there, 5, 2 is not there, 4, 6. 3 is connected to everything else, so nothing with 3. 2, 5, 2, 6 is 1. And then 1, 5. And I think we're done. Right, so this is now the complement of the graph G. Now, I notice here that it's fine that 3 is alone in the complement. And that's because in G, it was connected to all other vertices. Right? So that's fine. It happens. And you can probably guess at the relationship between the degree sequence of G and the degree sequence of G bar as well. Right, just look at this example and try it out yourselves. I'm not going to say anything about that in this video, but you can try exploring. And how does this help us with isomorphisms? Well, it helps us somewhat in the sense that, okay, if G and H are isomorphic graphs, then their complements have to be isomorphic as well. Okay, that sounds pretty obvious actually, right? If G and H have the exact same structure in terms of the adjacencies between vertices, what edges you have, then the missing edges, their structure will have to match as well. The edges that are missing from G and the edges that are missing from H. I'm not going to prove this formally in this video. This is another exercise that I'd like you to try proving on your own. But I just want to mention that where this may come in handy is maybe you have two graphs, G and H, that have so many edges for each one of them, such that looking at their complements might actually give you an easier time checking for whether they're isomorphic or not. All right, just look at this previous example. G had, I don't know how many edges is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. Well, G bar only has 5 edges, right? So comparing two graphs with 10 edges each, or comparing two graphs with 5 edges each, right? Fewer edges, slightly easier time, right? And that's, again, hypothetically, if you're comparing G to some other graph H that somehow had 10 edges as well. Right, and you're checking whether they're isomorphic. But yeah, I'm not going to do an example, but try proving this on your own.